What if every airliner had to fly on a single engine? The Airbus A380 is climbing through 28,000 feet over the North Atlantic when the number 2 engine explodes. Shrapnel tears through the nacelle. The crew shuts down the fuel, pulls the fire handle, and continues flying. This is textbook. Airlines train for this. The aircraft was designed for this. But now imagine something different. Imagine that from this moment forward, that single remaining engine on the left wing is all the aircraft has. No number 1, no number 3, no number 4. Just one turbofan, generating thrust, keeping 400 tons of metal and humanity from falling into the ocean below. This is not a drill. This is the question that sits at the absolute edge of aviation engineering. What if commercial aircraft could only fly on a single engine? The premise sounds absurd, even reckless, until you realize that modern aviation has been quietly moving toward this reality for decades. In the 1970s, twin-engine jets like the Boeing 767 were forbidden from flying long ocean crossings because regulators didn't trust them to survive on one engine if the other failed. Then something shifted. Engineers at Pratt & Whitney, General Electric, and Rolls-Royce began building turbofan engines so powerful and so reliable that a single engine could, in theory, sustain an entire wide-body aircraft in cruise. By the 2000s, the FAA granted ETOPS certification, Extended Range Twin Engine Operational Performance Standards, allowing twins to fly up to 330 minutes from the nearest airport on one engine. 330 minutes. That's 5.5 hours of single-engine flight over open water. We are already halfway there. But cruise flight is one thing. Takeoff is another universe entirely. When an Airbus A350 lifts off the runway, its two Rolls-Royce Trent engines are each producing roughly 84,000 pounds of thrust. Combined, that's 168,000 pounds fighting against gravity, drag, and a maximum takeoff weight of 617,000 pounds. If one engine fails at rotation, the remaining engine must not only provide enough thrust to climb, it must also generate enough asymmetric force to keep the aircraft controllable, while the rudder fights the massive yawing moment trying to spin the jet toward the dead engine. Pilots train for this scenario obsessively because it sits on a knife edge. The aircraft will fly, but only if the pilots react within 2 seconds, if the runway is long enough, if the weight is calculated perfectly, and if the air is cool and dense. Now remove the second engine entirely. What happens? The mathematics are unforgiving. Thrust-to-weight ratio is everything. A fully loaded Boeing 777-300ER weighs roughly 775,000 pounds at takeoff and relies on two GE90 engines producing a combined 220,000 pounds of thrust. That gives a ratio of roughly 0.28. Cut that in half and you're at 0.14. That is below the threshold for a safe climb gradient. The aircraft would not rotate. It would accelerate down the runway, eating up concrete, burning fuel, and simply run out of space. The tires would shred, the brakes would overheat, the fuselage would buckle. There would be no flight, only catastrophic structural failure at 160 knots. So engineers begin to adapt. If the scenario is permanent, if every airliner must fly on one engine forever, the first response is obvious. Make the engine bigger. Much bigger. The GE9X, the most powerful jet engine ever built, produces 110,000 pounds of thrust from a single nacelle. It is 11 feet in diameter, a tunnel of spinning titanium blades and carbon fiber fan casings that could swallow a Boeing 737 fuselage whole. Mount one of these on the center line of an aircraft, directly beneath the fuselage, and suddenly single-engine flight becomes plausible. The thrust is symmetrical. There is no yawing moment. The rudder is irrelevant. But now a new problem emerges. Where do you put it? Centerline-mounted engines are not new. The Lockheed L-1011 TriStar had one buried in the tail, fed by an S-duct that curved through the rear fuselage. The McDonnell Douglas DC-10 used the same configuration. But those were supplementary engines, not primary ones, and the engineering compromises were immense. The S-duct added weight, reduced airflow efficiency, and created maintenance nightmares. The tail structure had to be reinforced to handle the thrust loads, which drove up fuel burn. The L-1011 was an engineering masterpiece and a commercial disaster. It bankrupted Lockheed's commercial aviation division. Now imagine making that configuration the only option. The aircraft becomes heavier, slower, thirstier, and a decade behind in technology before it even enters service. The alternative is to shrink the aircraft. If you can't make the engine powerful enough, make the aircraft light enough. The Airbus A220, originally the Bombardier C series, is a narrow-body jet designed for efficiency, not size. Its maximum takeoff weight is just 150,000 pounds, and it's powered by two Pratt & Whitney geared turbofan engines, each producing 23,000 pounds of thrust. Replace those with a single engine producing 46,000 pounds, and the math starts to work. The thrust-to-weight ratio is 0.31, comfortably above the threshold. The aircraft could take off, climb, and cruise on one engine without violating physics. But here's the twist. It couldn't land safely at high-altitude airports. Denver International sits at 5,430 feet. Quito is even higher. Thin air means less engine performance and longer stopping distances. A single-engine A220 arriving at Denver in summer would need every inch of the runway. And if the engine flamed out on final approach, there would be no second chance. Redundancy is the religion of aviation. Every system has a backup. Hydraulics, electrics, flight controls, pressurization, all of it doubled or tripled. But an engine is not a wire or a pump. It is a controlled explosion producing 60 megawatts of power, spinning at 10,000 RPM, and enduring temperatures hotter than molten lava. Turbofan engines are the most reliable machines humanity has ever built, with in-flight shutdown rates below 1 per million flight hours. But they are not infallible. Bird strikes, volcanic ash, fuel contamination, turbine blade fatigue, all of these have brought engines to a stop. In 2009, U.S. Airways Flight 1549 lost both engines after striking a flock of Canada geese over New York City. Captain Sully Sullenberger had no thrust, no options, and 3 minutes. He ditched in the Hudson River, and everyone survived. In a single-engine world, there is no Hudson River option. There is only ground. The psychological impact would reshape the industry overnight. Passengers already fear flying, despite it being statistically safer than driving to the airport. The idea of boarding a jet with one engine, no matter how powerful, would trigger mass cancellations. Airlines would collapse. Insurance premiums would skyrocket. Regulatory agencies would demand impossibly high certification standards. Single-engine aircraft would need to demonstrate 1 million hours of flawless operation before carrying a single passenger. No manufacturer could afford the testing. No airline could afford the liability. The entire economic model of modern aviation depends on reliability through redundancy, and single-engine operation shatters that assumption. Yet the fantasy persists in aerospace engineering circles, not because it's practical, but because it forces a question. How much thrust can a single engine really produce? Hypersonic research suggests that scramjet engines, once operational, could generate thrust-to-weight ratios above 10-to-1, but those are for missiles and experimental spacecraft, not commercial transports. Turbofans are approaching their physical limits. The tips of the fan blades are already spinning near supersonic speeds. Push them faster, and shockwaves form, destroying efficiency. Make the fan diameter larger, and the nacelle becomes a parachute, generating so much drag that the extra thrust is canceled out. There is a ceiling, and we are nearly touching it. What this thought experiment reveals is that aviation has never been about single points of brilliance. It has always been about balance, redundancy, and managing risk across thousands of interacting variables. The reason we fly on 2 engines, or 3, or 4, is not because one engine can't do the job. It's because aviation does not tolerate single points of failure. The wing can flex, the fuselage can crack, the hydraulics can leak, and the aircraft will still land. But if the one engine stops, physics takes over, and physics is indifferent to human survival. We have built an industry on the principle that no single failure should be catastrophic. Strip that away, and we are not flying. We are gambling. And in aviation, the house always wins.